Homework 4, Team Job Security.
Dynamic range is a key parameter in electronic systems, but one that is often difficult to compare at the component level when trying to design a system for optimum performance. It is a specification that is often defined at the upper limit by a conceptual parameter known as the third order intercept point. Typically expressed in decibels or dBs, dynamic range is the ratio of the highest signal level a circuit can handle and the lowest signal level a circuit can handle. Several parameters can be used to define the highest level signal, such as the 1 dB compression point as well as the third order intercept point. The 1 dB compression point for an amplifier, for example, is where the linearity of the component begins to degrade. Under linear conditions, a 1 dB rise in input power will result in a 1 dB increase in output power. When the increase at the output is 1 dB less than the increase at the input, this is called the 1 dB compression point. The third order intercept point of a receiver mixer or amplifier is a mathematical concept. It relates the nonlinear products of the third order nonlinear term of a Taylor series expansion to the linear output signal of a component such as a mixer or amplifier. In some cases, a component's linearity may also be defined by its second order intercept point, which uses second order terms of a Taylor series expansion. In a receiver, the dynamic range extends from its third order intercept point at the high level end to the sensitivity at the low level end. The third order intercept point is a result of signal saturation and distortion effects, while the sensitivity is impacted by the thermal noise of the operating environment and the receiver's noise figure.
Precision and accuracy. The quality of the measurement of a single quantity, such as a position in range or angle, is characterized by its precision and accuracy. Accuracy measures the difference between the measured value and true value, while precision characterizes the repeatability of multiple measurements of the same quantity, even when the accuracy is poor. Thus, accuracy corresponds to the mean error, while precision is quantified by the error standard deviation. In radar, measurement errors are due to a combination of many factors, including interference such as noise and clutter, target phenomenology such as glint and scintillation, signal propagation characteristics such as multipath and turbulence, system measurement limitations such as signal quantization and signal sampling rate, and system uncertainties such as gain calibration, channel-to-channel phase calibration, and antenna pointing errors are all error sources that can impact both the accuracy and precision of the measurement.
So range resolution is the ability of a radar system to distinguish between two or more targets on the same bearing but at different ranges. The degree of range resolution depends on the width of the transmitted pulse, the types and sizes of targets, and the efficiency of the receiver and indicator. Pulse width is the primary factor in range resolution. For example, a well-designed radar system with all other factors at maximum efficiency should be able to distinguish targets separated by, as shown in the equation below, 1/2 the pulse width time. And so when you look at the figure 2, it shows that since the theoretical range cell of the system show fuck, hold on, we're good. And so below on figure 2, the animation shows two jets closely put together, and in it we can see that since this pulse width is not far enough, the two and how closely the jets are, when the pulse is transmitted towards the fighter crafts, it'll come back as a jumble of one single object, while in the second, the spacing for the second one shows a much farther apart, and so that makes it easier for the range resolution to pick up each of these aircrafts individually rather as a jumbled mess.